Okay, in this video we're going to look at factors that affect the strength of carboxylic acids. So this isn't explicitly mentioned or stated in the in AQA specification, and the video is going to essentially cross between the acids and bases topic and the carboxylic acids and derivatives topic, probably slightly more focused towards the organic chemistry, but its relevance to the strength of the carboxylic acids, so clearly related to the acids and bases topic. Like I say, it's not explicitly stated, but the reason for doing it is that in one of the sample papers that AQA produced before or right at the start of the teaching of this specification, there was a question which related to a fair chunk of what's in this video. But also, I think another reason that makes it worthwhile is that it will enrich and remind you of various features of organic compounds that are relevant to other homologous series, for example, with amines. So in amines, we have to appreciate and understand the reasons behind their different strengths as bases, so understanding the reasons for the different strengths of carboxylic acids is going to be relevant to that. So I'm going to start with the Ka and the acid dissociation constant and our expression for that. Ka is, and this is derived from the equilibria expression. So obviously H plus is the hydrogen ion and A minus is the salt. So if we were looking at carboxylic acids, it would be the carboxylate salt, and then HA would be the carboxylic acid. And if we just compare the Ka values of two acids that we're familiar with, one thing to say is the larger the value of Ka, then the stronger the acid must be, because a larger value of Ka means that the numerator is greater. And if the numerator is greater, that means the concentration of hydrogen ions is greater. And if the concentration of hydrogen ions is greater, then the acid is clearly a stronger acid. It's going to have a lower pH. So the larger the value of Ka, the stronger the acid. And if we look at a strong acid like nitric acid, it has a Ka value of about 40 moles per decimeter cubed. And if we compare that with ethanoic acid, what we consider a weak acid, we can see that the ethanoic acid value is much, much smaller. So the Ka value shows us very clearly that nitric acid is a much, much, much stronger acid than ethanoic acid, 10 to the 5 plus times stronger. So that's an easy conclusion to draw. But that's just to remind us about Ka, and it's just to remind us about how Ka is a reflection of how strong an acid is. So another way that we can look at it is we can take the minus log of Ka, so that would be pKa. So we can also measure the strength of weak acids on a pKa scale. It's probably easier because we've got much more manageable numbers. But because it's a minus log, just like with pH, the lower the number, the stronger the acid. The smaller the number here on a pKa scale, the stronger the acid is. So we're going to compare ethanoic acid with ethanol. So ethanol is not something we consider to be an acid, but it would still have a Ka value. And we can see that there is, we know that this is a log 10 scale, so there's a significant difference between ethanoic acid and ethanol. The ethanoic acid pKa value is much lower than ethanol's. So, again, unsurprisingly, given that ethanoic acid is considered an acid and ethanol isn't, generally speaking, then ethanoic acid is a stronger acid than ethanol. But it's worth now unpicking this a little bit further, because if we look at the structures of those, if we just look at the structures of those two compounds, and we consider what's happening, or we consider the equilibria, if we're thinking about their equilibria, if we're thinking about their sort of acid strength, then what we're considering is the same bond. So in both cases, if we're considering how strong an acid, then we're considering how easy or not it is to break the oxygen-hydrogen bond, because that's where the dissociation is taking place. And it's the same, it's an OH bond in both cases. So we have to consider why then is there such a big difference in their PKA values. So two factors that influence the ionization of an acid, so influence that dissociation. And there are two factors. One is the strength of the bond being broken, which is not a surprise given that we have been talking about the fact that it's breaking that bond that is the dissociation. But actually something else that you might not have considered, another factor, is the stability of the ion that's being generated or formed. So both of those factors are in play when we're considering or trying to gauge how strong an acid is, or if we're trying to understand the difference in the strength of two carboxylic acids. So if we look at the carboxylic acid, what we've got, if we consider what those structures were and we think about what's the same and what's different about a carboxylic acid compared to an alcohol, is that we've got that electron withdrawing carbonyl group. And that carbonyl group is going to withdraw electrons away from the H atom in the hydroxyl group. And the consequence of that is it's going to weaken the OH bond. And therefore, if it's a weaker bond, then it's easier to break. So you're going to have a greater degree of dissociation. And therefore, the concentration of hydrogen ions is going to be greater. So key difference between an alcohol and a carboxylic acid is that we've got the carbonyl group in the carboxylic acid. That's electron withdrawing. It's going to weaken the OH bond, the bond that needs to break. So it's going to break more easily. So we're going to get a greater degree of dissociation. So we're going to get an increase in H+ ions. And this was in the sample question, although it was about a different compound, or the comparison of two different compounds. It was focusing on electron withdrawal and the weakening, the greater dissociation, and the weakening of that OH bond. So the strength of the bond being broken is a factor, but equally the stability of the ion being formed is a factor. And this is where, with the help of sort of evidence, so there is our carboxylate ion. This is how we would typically write it if we were showing our equilibrium, we were doing structural formulae. That's how we would typically write it. But X-ray diffraction studies, so that's where they actually look at the structures of molecules. Have actually shown that the two carbon-oxygen bonds, so what we think of as this and what we think of as this, are actually of equal length. So that's a bit of a surprise, right? That doesn't match the sort of representation that we've got here. To say that those two carbon-oxygen bonds are of equal length does not match that representation. Not only that, but what we also discover is that that length that they both have is shorter than a carbon-oxygen single bond and longer than a carbon-oxygen double bond. It's sort of somewhere in between. So one of the things that suggests is that the negative charge, what we currently are showing here as being just on one of the oxygens, is actually distributed evenly across or over that carboxylate part of the molecule, so over the COOs. So it's being evenly distributed over the two. So this is a nice sort of little diagram, but it also shows the bond lengths. So we can see the bond length of a carbon double bond oxygen is 1.2 angstroms. Carbon oxygen single bond here is 1.34, and then what they've discovered in the X-ray crystallography is that the carbon oxygen bonds are both the same, and they are both 1.27, which coincidentally is sort of halfway between these two values. And so what's happened is the extra pair of electrons, or the lone pair that we would have shown to represent all, is now distributed across the carbon oxygen. So there's a delocalization. So a little bit like well, it's in a pi bond, so it's a little bit like our alkenes. So we've got overlapping p orbitals, and the electrons are sort of being distributed now over essentially 3 atoms, although obviously they'll be much more concentrated towards the oxygens because they're more electronegative. So that delocalization makes the ion more stable. And then, so there's another visual representation of there. So we've got a single negative charge now distributed over more than one atom. And that if it's that actually makes it then less open to attack. So we're talking about a comparison here. These are relative differences. So it's less open to attack by H+ ions and therefore is less likely to reform the original molecule again. And with our alcohol, we would have had that that minus charge just solely on the oxygen. That was the oxygen of the OH bond. So it would have been much more open to attack by H+ ions. So you've got to think that your equilibria is in both directions. So you haven't just got the dissociation of the OH bond, you've got the reforming of it, or the formation of that OH bond going in the going from right to left. So let's have a look at some PKA values. So there's quite a few here. You might want to pause the video and just have a look at them. But what I'm going to do is I'm going to break this up into parts. So these are all carboxylic acids. So up to this point, we've just been explaining the difference in strength between a carboxylic acid and an alcohol. But here now, all of these are carboxylic acids, but they quite clearly have different strengths. Okay, so some are much more acidic than others, or some are much further to the right of the equilibrium or equilibria than others are. So just to start with, I just want us to focus on these three. So we've got 2-chloroethanoic acid, we've got methanoic acid, and we've got ethanoic acid. And you can see that the 2-chloroethanoic acid is the strongest acid of the three, and ethanoic acid is the weakest. And now I just want you to pause the video and have a think about what factor, what is it that's different about them, and that is going to explain this difference in the strength, in their acidic strength, and how are you going to explain it? And think back, try and apply that, try and apply your idea to the strength of the OH bond and also to the stability of the carboxylate ion. So because really the factor should be relevant to both of those. So I'm just going to pause the video, have a think. All right, so let's focus on the strength of the OH bond to begin with. So just going to draw the three structures, sorry. So we've got our 2-chloroethanoic acid, we've got our methanoic acid, and we've got our ethanoic acid. I've already given a massive clue there with something that I've already annotated on those structures. So what we can see is we've got a chlorine group attached, which is electron withdrawing. It's an electronegative, or particularly electronegative element. So it's going to be drawing electrons towards it. It's going to have that delta plus, delta minus between the carbon and the chlorine. With the case of methanoic acid, we're treating this as the hydrogen is neither withdrawing nor donating. We're saying that because we're comparing it to what else is attached in the other two compounds. And then, like when we did carbocations, one of the things that we knew about alkyl groups is that they were electron pushing or electron donating. So we can sort of represent that with the arrow going from left to right. So what does that mean? Why does that have an effect? So what's happening by having that electron withdrawing group, what the consequence of that is that the OH bond is becoming more polarized. So remember, these are relative to each other. So they're more polarized. So for the sake of this, whilst we only ever write delta plus, delta minus, because I want to make a comparison, I'm just going to refer to this, the difference in the partial charges here is delta minus 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 and delta plus plus plus. So we've got a more polarized OH bond, and so it's going to be easier to break. There's going to be greater dissociation. With the methanoic acid, we're not talking about withdrawing or donating, so it's going to be it won't be as polarized as in the 2-chloroethanoic acid, but I'm going to show it as delta minus minus and delta plus plus. And then when we look at the electron donating structure, we've got now something even less polarized, with the OH bond is even less polarized, so there is even less dissociation into H+ ions, and it's still got the partial charges, but compared to the other two, those partial charges are not as different. Okay, so that bond is less weak, or the bond is stronger comparative to the others, so it's harder to break, and so we get our trend in terms of the strength of acid. So having an electron withdrawing group is going to make an acid, carboxylic acid, stronger. Having an electron donating group is going to make it weaker. So that's about the strength of the OH bond, but what about the stability of the carboxylate ion? So here is our carboxylate ions, or here they are. So I've got the three of them there. And again, I can say electron withdrawing, neither withdrawing nor donating, and electron donating. So how does that affect the stability of the carboxylate ions? Well, if we're drawing electrons away, then we are in effect making this minus charge, which is already spread over more than one atom, that little bit smaller. And if we're making it a little bit smaller, so I'm saying less negative charge, what I'm saying is that this minus charge is now, some of it is just being pulled towards the other end of the molecule, so it's just being lessened around this area, then that's going to make it even more stable because it's going to be even less attractive to an H plus ion. Methanoic, that's all like our, I don't know, that's the standard against which we're measuring the others. If we look at the carboxylate ion that is from, or the ethanoate ion, then we can see that we're actually pushing more electron density, or pushing more negative charge, if you like, towards where the sort of carboxylate part is. And so we're making that minus charge that little bit bigger. So that's going to make it that bit more attractive to the H plus ion, which means it's less stable. So I'm using the words less and more because I'm making comparisons. But so we can, with exactly the same factors, explain how the OH bond is stronger or weaker relatively, and how the carboxylate ion is stronger or weaker, and they marry together, those two things marry together. So we can still see that we have the stronger acid with the electron withdrawing group and the weaker acid with the alkyl group. Just to go back to that table and look at a few more comparisons. If we just look at these two, so we've got 2-chloro, ethanoic acid, and 2-iodo, and we can see there's a difference in the PKA value. We can see the 2-chloro is a stronger acid. You could have a think about why that difference is for a moment. So maybe just pause the video. So what is our independent variable here? Our independent variable is the halogen that's attached, and then our dependent variable is the strength of the acid. So why is the chlorine making it a stronger acid than the iodine? And it's simply because chlorine is a more electronegative element, so it's going to be more electron withdrawing than the iodine. Okay, so we're making a sort of a comparison there between those two elements. If we look at the ethanoic acid and ethanoic acid, we can see there's a huge difference there. And the way to approach this would actually, the ethanoic acid would actually have two Ka values. So it would have a Ka value for the removal of one oxygen, and then there would be a Ka value for the removal of the second. So you've got to see this as two equilibria, or a sequence of equilibria, perhaps is a better way of phrasing it. So when we're making the comparison, this is the first Ka value, or the first pKa value. We've got to focus on the fact that the bond that's dissociating is this oxygen-hydrogen bond, and the same here. So then we're treating the other carboxylic acid group not in this instance as an acid group, but as something that is electron withdrawing. So this C double bond OOH is an electron withdrawing group as far as we're concerned here. So it weakens the OH bond and stabilizes the carboxylate ion. And clearly that second carboxylic acid group has a greater effect than having a halogen attached. Just final things, if we just compare these two here, so they're the same length chain, so the same size alkyl group, so it's we've got, what have we got, 3-chloro butanoic acid and 4-chloro butanoic acid, and we can see that 3-chloro is stronger, and essentially what we've got is the closer that our electron withdrawing group is to the carboxylic acid group, the greater the effect it has. So we've got it on the third carbon, we've got it on the fourth carbon, so clearly when the chlorine is on the third carbon, it's going to have a greater effect. I think that reintroduced or reminded us about electron withdrawing, electron pushing, or electron donating. It reminded us about PKA and Ka. And like I say, there has been a question in a sample paper, and it was a 6-mark question as well, which was to do with this. The answer that they gave in the mark scheme focused on the strength of the OH bond, but they equally should allow the stability of the carboxylate ion. They are both relevant factors, and they both have the same basic explanation. So I hope that was useful, but if you